We're working with symmetry today in pre-calculus, and we begin by identifying there's three forms of symmetry. We have line symmetry, which is a reflectional form of symmetry that usually happens with either reflecting across the x-axis or across the y-axis. And then we have rotational symmetry, specifically of 180 degrees, which is also called point symmetry. And that's what we see when we have symmetry rotated around the origin. This is visually seen by flipping your paper 180 degrees and seeing that the shape looks the exact same. When we have line reflection, line symmetry over the x-axis, if we have a point x comma y, what other point must be on that graph?
Negative.
Still x, but now the y goes negative. So here we're going to put x comma negative y. That has to be on this graph. And therefore, what lets us algebraically test if it works is when we take y and replace it with negative y. And it results in the equivalent equation. We'll do some examples of that in a few minutes. Similarly, when we have y-axis symmetry, we're talking about a traditional parabola being one example. If we know that the point xy exists on the shape and it has symmetry across the y-axis,
Yeah.
good. This one would be negative x comma y, must also be on that graph. Which means we can validate this or prove it algebraically by replacing x with negative x and seeing that it gives us the same y. And origin symmetry, which is the rotational of 180 degrees. If this point is xy, what point must also be on that curve? Good. Negative x, negative y. So if this point is on it, so is negative x comma negative y, which means we can validate it, but we have to do both. We have to replace x with negative x and y with negative y. And they have to result in equivalent equations. What does that mean? Well, let's do some examples here. If I take a look at this visual, this graph, what would you say is the symmetry across the x-axis, y-axis, or origin? Y-axis, good. Now, if we think it has y-axis symmetry, we should be able to come up here and say, okay, y-axis symmetry, we should be able to replace x with negative x and get the same thing. So if I take this equation that I started with, y equals, but instead of x, I put in these parentheses as placeholders, and I replace each x with negative x. And then I simplify. If I take negative x to the fourth power, what happens to this term? Becomes positive x again, doesn't it? X to the fourth. Minus 4 times negative x squared. I do the exponent before I do the multiplication. What happens to negative x squared? Positive x squared. So it stays to be negative 4x squared. Is this resulting equation the same as what we started with? It is. That validates for us that, yes, let's say verified, that it has y-axis symmetry. Take a look at number 2. Looking at the graph, what do you think is the symmetry? Good. Origin symmetry, right? Rotation of 180. It doesn't reflect just across the y. It doesn't reflect just across the x. But if you flipped this upside down, it would look the same. if I want to test for origin symmetry, I have to replace both the x with negative x and the y with negative y. So I make parentheses for the x and the y. Instead of x, I put in negative x. Instead of y, I put in negative y. And what happens when I do negative x times negative y?
XY?
Xy. The negatives become positive. So xy equals 6. How does that compare to our original equation? It's the same. That validates that having made this change, putting in x and y for negatives, verified that this is in fact origin symmetry. How's this feeling? 5. Actually, this makes a lot of sense. 3. It makes some sense. 1. That's not sense. It's something else. Good. Very good scores. Sadly, those of you online, you didn't get the whole experience with the graphing calculators, so might make less sense to you. Let's take a look at number 5 here on the backside, second page. Looking at that picture, what do you think it might be? What might be the symmetry? None? Are you tempted to think it's origin symmetry?
No.
Why not?
Oh, we're looking at that.
Number 5. So what is the x-intercept here? 1 comma 0, right? And if I flip it upside down, that 180 swing, what is it now?
Yeah.
Negative 1, 0. So it's close to being an origin symmetry, but it's actually been shifted over a little bit. So this is a none. Now, the question is, if it's none, that means that we've validated that it's not x-axis, it's not y-axis, it's not origin. What I recommend you do for these things is you take all 3 cases. Consider this as f of x. We're going to do it again down here, but I'm going to bring it to you early. Let's call this f of x equals cube root of x minus 1. Are you all okay that that's the exact same thing, just with different notation? So now I've established what f of x is. It's the original thing. We didn't have to do anything to it. Now I'm going to try switching the x. In other words, I'm going to call it f of negative x, which means I'm going to have the cube root of negative x minus 1. Is there anything I can do to simplify that? No? I mean, theoretically, because it's a cube root, I could pull the negative out, like pull out a negative 1, because negative 1 would be the same as negative 1 times negative 1 times negative 1. So I could theoretically pull that out and call it negative cube root, but then this would become x plus 1 on the inside, because I'd be pulling out the negative from both parts. And now let's try the third choice, which is if I distribute a negative across the whole function, I make it negative y, then that would be where now it's negative in front, but the inside would have to stay the same. And then I want to compare all 3 of these. If all 3 of them come out this, or excuse me, if any of them come out the same, then we've got some symmetries. If none of them come out the same, then we don't have symmetries. Can we agree those are all different? Yep, so that's verifying that it's none.
It's none.
Yep, that has no symmetries. I'll leave these additional examples for you to do as homework. Let's move on to an extension on this, which is that we can classify functions as even or odd. A function is even if it is symmetric with respect to the what?
Axis?
Well, what's a good example of an even exponent?
Oh, y-axis.
Our parabolas, right? X squared, and that has symmetry with respect to the y-axis. And again, our points are x, y, and negative xy. So this is the case where you take x and replace it with negative x. A function is odd if it is symmetric with respect to the let's see, an odd number like y equals x cubed. Good. Origin is correct. And this point of xy suggests that there must also be a point of negative x, negative y. So this is where we'd have to change both of them. Negative x, negative y, excuse me, negative x, x to negative x, and y to negative y. But I'm also going to write over here what we just talked about, that if I plug in x as negative x, it comes out the same. That means that f of x is equal to f of negative x. F of x is equal to f of negative x. And then this one says, if I take x and replace it with negative x, then my y ends up being the opposite as well, negative f of x. So this time I've got a negative in the x on the left and a negative in the overall function, the y, on the right. So we're now going to determine whether a function is even, odd, or neither using this idea. Step one, we've already got f of x. Let's give ourselves f of negative x. That means I take my x values every time they show up and I replace them with negative x. And I simplify. What does this become?
Negative x.
Good. Negative x cubed. What does this become? Positive x, because this negative times this negative makes it positive. So in other words, we know that f of negative x.
Wait, so it's different. Doesn't work out.
Well, you're right. This is not the same as this, but we're not done yet. We still have to do the third part, which is where we say negative f of x. When I do negative f of x, I simply take the original function and I distribute a negative 1 across it. So that's negative x cubed plus x. And then we compare. We say, are any of these the same?
No.
We're looking at the right-hand sides. Do we agree that this one and this one are the same? Therefore, we've discovered that f of negative x is equal to negative f of x. That's this one. This is odd. And does it also work with the trick I gave you? X raised to the third power, which is an odd number, x to the first power, which is an odd number. It's all odd exponents, so we expect it to be odd. But again, that won't work for everything. It's going to work for this unit. What do you expect is going to happen here over with 8?
Either.
Good, even. Let's try it. We've already got f of x.
Either, because it's like 1. Well, that doesn't have a very, so, this is only 2 squared.
So this is like x to the 0, really.
Yeah.
And 0 is more even than odd. So I'm going to have negative, and then instead of x squared. And the whole trick here is, why does this work? Because when I put in a negative x and I square it, it goes back to being what it was before I changed it. If there's a fourth power there, it goes back to being what it was before I change it. If I don't have an x, then I'm not putting a negative x in there. So it goes back to what it was. So this is the same as negative x squared plus 6. And then we try the third choice, which is distributing a negative across the function, which makes it positive x squared minus 6. That's different.
Wait, so
But these two are the same.
oh,
Yep.
so it's even.
Sorry, hold on. Let me go again.
Well, you have to.
This one here, exponents first before we do the multiplication. And so because we see that f of x is the same as f of negative x, that tells us it's even. Okay, that concludes our discussion on symmetry and even odd functions. Please finish this packet as homework number 5.
Wait, what about the other side? Are we doing the other side?
Finish the whole packet, please.